On September 19, 1985, a magnitude 8.1 subduction zone great earthquake occurred beneath the coast of Michoacan, Mexico. Despite the 350-kilometer distance from the earthquake epicenter to Mexico City, most of the 9,500 fatalities and 30,000 serious injuries occurred there. That earthquake prompted Mexico to both strengthen its building codes and to develop an earthquake alert system for all of southern Mexico. To understand how a subduction zone earthquake could cause such devastation so far away in the Mexico City basin, let's start by looking at the tectonic setting. The Cocos Plate dives beneath the North American Plate at rates of 5 to 7 centimeters offshore of Michoacan, Guerrero, and Oaxaca. The 2,700-kilometer-long Middle America Trench marks the subduction boundary from southwestern Mexico to Costa Rica. In the past 40 years, Mexico has had 50 earthquakes larger than magnitude 6, with epicenters concentrated near the plate boundary. During that interval, a dozen magnitude 7 or larger earthquakes occurred in the subduction zone. Red circles mark epicenters above the site where fault rupture began, and yellow shows the rupture area. The Guerrero seismic gap is a potential hazard zone. How can we understand the relative energy released by a great earthquake of magnitude 8 or 9, like the 1985 earthquake, compared to smaller yet still damaging earthquakes? The energy released by earthquakes increases by a factor of approximately 32 for each unit increase in magnitude. As an analogy, if breaking a single strand of spaghetti represents a magnitude 5 earthquake, then we need to break 32 to represent a magnitude 6, 1,024 for a magnitude 7, and nearly 33,000 to represent a magnitude 8. To represent the energy released in a magnitude 9 earthquake, like Japan in 2011, we would need to break more than 1 million noodles. Chile in 1960 was even bigger. Most people think of an earthquake as a sudden release of energy at the epicenter. In reality, an earthquake is caused by sudden displacement of rock across a fault at a given depth within the Earth at the hypocenter, shown in this view of the top of the subducting plate. For great earthquakes, the displacement at the hypocenter is just the beginning. In 1985, the rupture displaced an area 180 kilometers long. Let's zoom in now to a cross-section to view the plate interaction. The dense oceanic plate dives beneath the more buoyant continental plate at a rate of about 6 centimeters a year. Because tectonic plates are elastic like a spring, converging plates build energy at the leading edge of the continent. Locked by friction, the upper plate is forced back and shortened, raising the land surface. GPS, not available in 1985, is now able to measure that strain. During a megathrust event, the force of the converging plates overcomes friction and causes the overriding plate to move up the fault surface. If it breaks up all the way to the trench, as it did in Japan in 2011, the leading edge will lurch seaward, uplifting the seafloor and forming a mound of seawater that spreads out as a tsunami. The disaster of 1985 surprised seismologists who thought a subduction zone earthquake would not produce such sudden ground motion or strong accelerations 350 kilometers away in Mexico City. Here's why. If the seismic waves were traveling through uniform material, shaking would be half as strong at 13 kilometers, a quarter as strong at 27 kilometers, and an eighth as strong at 50 kilometers. Mexico City recorded up to 1 g of acceleration, a velocity demonstrated in this shake table experiment, whereas Acapulco, on bedrock closer to the epicenter, had only moderate shaking. What explains the much stronger ground shaking in Mexico City? Mexico City sits on the remnants of a dried-up lake that once surrounded the Aztec capital, Tenochtitlan, now a sediment-filled basin surrounded by hard volcanic bedrock mountains. Short-period seismic waves produce weak ground motion as they pass through the bedrock, but once inside the lake basin, the waves slowed and were amplified, causing the soft sediment to shake like jello in a bowl. In the broad Mexico City basin, seismic waves became trapped and reverberated for many minutes in a phenomenon known as Basin Amplification, as the waves bounced off the bedrock, becoming slower and bigger in the sediment. The sediment resonated with a 2-second period for over a minute. The period of oscillation, or shaking, is a time between two peaks. In the bedrock, seismic waves oscillated with a 1-second period but slowed to a 2-second period with higher amplitude as the waves reverberated in the basin. Before earthquake codes, buildings were not always engineered to withstand back and forth accelerations. All buildings have a natural period, or resonance, which is the number of seconds it takes for the building to naturally vibrate back and forth. If the period of ground motion matches the natural resonance of a building, it will undergo the largest oscillations possible and suffer greatest damage. Small buildings resonate naturally in the 1-second period. A high-rise building, on the other hand, naturally resonates with a longer period. For example, a 30-story building resonates at a period of 3 seconds, and a 50-story at a period of 5 seconds. The result of the 2-second period was that of buildings of 18 to 20 stories with similar natural periods suffered the most damage, while short buildings and skyscrapers were relatively undamaged. In 1991, seismic stations were deployed only in the state of Guerrero, an area identified as the most hazardous for proximity to Mexico City, and the seismic alert system was initially designed to provide warning only to Mexico City. It has since been expanded to issue warning to all large cities in the coverage area. These 100 seismograph stations are the backbone of the seismic alert system, as they detect and record ground motion and transmit the data to a central control system that rapidly analyzes the data to determine magnitude and location. For a moderate-sized event, a preventative warning goes out only to government authorities and select users like hospitals and the Mexico City subway. For larger earthquakes, a broader alert is broadcast via TV, radio, and loudspeakers to notify people of impending shaking. On April 18, 2014, the seismic alert system was put to the test. A magnitude 7.2 earthquake just north of the Guerrero Gap was recorded by coastal seismometers that immediately determined the epicenter, depth, and magnitude. The large size automatically prompted a public alert to be issued to all cities within the coverage. The 18 million people in the Mexico City basin received their earthquake early warning 71 seconds before ground shaking arrived. In 71 seconds, people can move to safety, machinery can be shut off, rail and road traffic stopped, and emergency personnel and equipment ready for response. Public education has been essential to the success of this program.